Hello and welcome to our videos on trigonometry for grade 11 brought to you by the Answer series. You may find it useful at this point to watch or re-watch the trig theory revision video on graphs, as this video builds nicely on the basics covered there. We are now at the fifth of our 6 trig concepts in this video series. And in this video we will look at an extension of what we covered in the theory videos as I mentioned. Firstly, by considering the concept of the amplitude of a trig graph, then the concept of the period, and then also the shifting of a trig graph both up and down and left and right. As we go through each of these, we will look in all 4 cases at what in the equation impacts each of them. First though, let's check in on how they each affect the sketching of a graph. The amplitude is the distance either side of the center or midline. The period is the number of degrees for one complete wave. The up and down shift is when the graph as a whole moves up or down because of a change in the y value. And the left and right shift impacts where the wave of the graph starts because of a change in the angle. You will see as we go through each one of these concepts that I have used the sine graph to illustrate the effect on the sketching, but of course the concepts also extend to cos and tan. So let's start by having a look at what influences the amplitude of a graph. Remember, the amplitude is the distance either side of the center line or midline, and it is the coefficient of the ratio that we need to observe. The amplitude of a standard sine graph is 1, and of y equals 2 sine x is 2, and of y equals a half sine x is a half. Let's have a look now at illustrations of each of these 3 graphs. So here we have the 3 graphs, y equals sine x, y equals 2 sine x, and y equals a half sine x. Remember that a trig graph is based on an equation in y and x and is represented on a Cartesian plane, and so everything we know to be true for graphs and functions is also true for trig graphs. Let's quickly recap the 3 basic facts about graphs that could help us here. First, that every point on the graph makes the equation true. Then that x is 0 on the y-axis and y is 0 on the x-axis. And thirdly, each graph's shape is unique as a result of its equation. In other words, the results of a particular pattern will produce a particular type of graph. And so let's check in on a few points here to confirm the pictures we see. Let's consider a few x values and check the corresponding y values. So if x is 0 in each case, then because of the sine of 0 being 0, the y will be 0 for each one. The same will be true for x being 180 degrees, so let's look at what happens in each case for when x is 90 degrees. Well, here y will be sine of 90, which is 1, and for y equals 2 sine x, y will be 2 times sine of 90, which is 2 times 1, and so y's value will be 2. And for y equals a half sine x, y will be a half times sine of 90, which is a half times 1, and therefore y's value will be a half. This shows then nice and clearly that the coefficient of the ratio is in fact the amplitude of that graph. Let's think for a moment now about cos and tan. Sine and cos behave very similarly, and so the thinking for the amplitude of cos will be similar. But for tan it is different because tan doesn't have a maximum or minimum value, and this means that there is no amplitude for tan, but it is still helpful to notice the effect the coefficient of the ratio has on the sketching of tan. Again, by taking values of x and finding their corresponding y values, you'll be able to see that the coefficient will stretch or compress the graph according to its value. Now for the period of a trig graph, again we will look at sine. We know that the number of degrees for one full wave of a standard sine graph is 360 degrees, and so 360 degrees is therefore its period. What happens then to the period when the angle is more complex? Well, it's the coefficient of the x that impacts the period, and we can use this coefficient to help us calculate this adjusted period. Let's have a look now at how these changes impact the standard sine graph. So here we have sketched each of the 3 graphs we just mentioned, and over here for each we have highlighted the number of waves within a 360 degree interval. The standard graph, as we said, has one wave within this interval. Then if we look at the graph of y equals 2x, this has two waves on this interval, and the graph of y equals a half x has a half a wave. It is maybe fun to remember this as what you see is what you get when considering the coefficient of the x, but it is always a good idea to ground your knowledge in solid understanding. Let's take the same approach here as before by taking a couple of x values and checking their corresponding y values. Again, if x is 0 for each, then y will be 0 in each case. What about when x is 180 degrees? Well, here, y will be sine of 180, which is 0. And for y equals sine 2x, y will be sine of 2 times 180, which is sine of 360, which is 0. And for y equals sine of a half x, y will be sine of a half times 180, which is sine of 90, which is 1. Hopefully now you are convinced that these graphs are a true reflection of their equations, so now let's confirm their periods, which we looked at algebraically before. When we have one wave in this 360-degree interval, the period of the graph is 360 degrees. When we have two waves in this interval, the period of the graph is 180 degrees, and when we have half a wave in this interval, the period of the graph is 720 degrees. If we think now of cos and tan as well, the period of cos behaves similarly to sine, but again tan is different, and it's different in that its standard graph completes a full wave within 180 degrees, and so tan's standard period is therefore 180. It is just the starting point, however, that is different for tan. Otherwise, calculating the adjusted period for tan follows the same logic. Moving on now to looking at the shifting of a trig graph, we'll start with the up and down shift. This shift happens when there is a change in the y value, in other words, when something is being added to or subtracted from the right-hand side of the equation. Let's take the standard sine graph and add 1. What is essentially happening here is that each of these y values increase by 1 unit. In the same way, if we subtract 1 from the standard graph, each of these y values decreases by 1 unit. We can know, therefore, that the constant term indicates that there is an up and down shift, and by how much. Let's go on now to see what this looks like. As you can see from these graphs, the standard sine graph moves up 1 unit as a whole when 1 is added to the equation, and the entire graph moves or shifts down 1 unit when 1 is subtracted from the equation. It's also useful to be aware that when there is an up or down shift, then the range of the graph, which is the set of y values for which it exists, will change. If we look now at the left and right shift, here the change in the equation happens within the angle. In other words, if something is being added or subtracted to the x in the angle, then the starting point of the graph will be different. The new beginning can be established by finding which value of x would make this bracket 0. This particular value of x will then give us our new starting point. Again, starting with a standard graph of sine, let's focus here on its starting point. Sine of 0 degrees is 0, and therefore one of the waves of the sine graph starts at the origin. If we go across here now to look at y equals sine of x plus 30, we can see that the value for x that makes this bracket 0 is minus 30, and so our graph shifts to the left with the start of the sine wave being at minus 30 degrees. And over here now, with y equals sine of x minus 30, the x value that makes this bracket 0 is 30 degrees, and so the sine graph moves to the right with 30 degrees as the start of the wave. In each of these situations, the graph will continue from this point in both directions according to the amplitude and period of the graph that the equation indicates, and the required interval will be provided for you in the question. I like to encourage finding the starting point of the graph using this method rather than trying to remember something like plus means shift left or minus means shift right. Again, making sure to ground your understanding in something more concrete. Once you feel comfortable with the theory of the concepts covered in this video, then pop into our study guide to try some examples. Applying theory as soon as possible gives it the best chance of settling and becoming knowledge you feel confident about.
Check out the video description below for practice questions from our study guides. If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.